Go ahead.
Part of my dissertation had inhomogeneous and homogeneous.
Okay, so your dissertation you use homogeneous.
Homogeneity. Yes.
Exactly.
Wait, we got to get this right. So Athena's going to be the tiebreaker, so hang on. Dr. Kroon, you say what?
For this particular word, homogeneity, and homogeneous for it's the other version of that.
Okay, and Landon, do you agree?
Yes.
Homogeneity? Okay, Athena?
Yep, homogeneity.
We're going to go with homogeneity then. Okay, sounds good. Right. This is how myopic we get on this program. We have to make sure that we pronounce homogeneity correctly. All right, next slide. She's never coming back, people. Okay, next slide. He's like, what am I getting myself into?
I'll make a whole video about homogeneity.
Exactly. We might have started a whole new series, the homogeneity series. Okay, so the homogeneity problem, the solutions were the cosmic inflation model, which we had talked about. And I think you mentioned, obviously, the variable speed of light model. You kind of touched on that they were kind of playing around with if the speed of light can change, that would kind of solve this issue, right? And the reason why we pick one over the other is because there's really no evidence that the speed of light has changed. Would that be a fair summation?
Yeah.
Okay. Yes, I mean, by the way, you mentioned like the fine structure constant, other things. It would be relative as would be observing a radically different universe if the speed of light were variable. And so the two possible solutions, cosmic inflation and VSL, considered, but observational evidence favors inflation model and not variable speed of light.
You're breaking up a little bit, Landon, but yeah, we got most of that. We got most of it.
Sorry,
the younger creation out there.
Yes.
Just hang on. The younger creation out there, there's a couple of them watching. Pay attention to this because this shits all over younger creationism right now. So just bear in mind that when they talk about things like accelerated decay, they talk about things like asynchronous light. Yeah, not going to happen. So because we exist, and
there
if
is
those things
zero.
Were true, we would not exist.
There's zero evidence that the speed of light in a vacuum changes.
And that's good that you mentioned that because we are talking about C, which is speed of light in a vacuum. Speed of light is a constant in a vacuum. Can light be slowed in various mediums? Yes, of course, but that's not what they mean by changing the speed of light. All right, next slide. The monopole problem. A large number of very massive, stable magnetic monopoles, theoretical particles with a net magnetic charge, basically a magnet with one end, could have been produced early in the universe due to spontaneous symmetry breaking from a single gauge theory. Why have no stable monopoles ever been observed? Now, I'm going to turn this one to Landon, because Landon kind of rewrote this. I had my version of it, but he wrote it. Why do we have to care about the monopole problem, and what actually is it in relationship to the Big Bang?
Well, there's a thing called gauge theory that would state that we should have these particles, theoretical particles, with a net magnetic charge that should have been created, and the assumption is that these particles, should be out there. So people went and looked for monopoles, and the problem was that we're not finding them. Now, are we not finding them because we don't know how to look? Or we're not finding them because they don't exist? Or we're not finding them because they're rare? Well, the way that the universe, again, there should have been massive stable monopoles according to the models that we use, and we don't see them. So what happened?
Now, that doesn't mean they don't exist. Correct me if I'm wrong. We've discovered monopoles. We've discovered decay things in monopoles, but they're induced. Either they've been produced somehow. They're not primordial monopoles that we're talking about, because those would have long since decayed. But we have discovered monopoles exist, right? Anybody?
Not to my knowledge. That would be
not to my knowledge. I don't know.
Okay, I've read things up. They found decays that they would expect from a monopole. So I have read things out there that if it discovered that these monopoles do exist, but they're not primordial. Now, I could obviously be completely wrong on that, but we'll have to look into that. But from what I remember reading, they did find decays that they would expect from monopoles, what they would if they did exist.
Could you maybe have been thinking about condensed matter physics monopoles,
No.
which is a different?
Yes.
Well, I mean, possible. I mean, the way I look at condensed matter. Condensed energy is matter, and then condensed matter would be like Einstein's Bose constant, right?
Yeah.
Very, very cool cryogenetic stuff. Helium frozen down to absolute zero, that kind of stuff.
Yeah.
I think that might be it. I mean, because do they have things that are basically what we would look for, what a monopole would look for in those kind of condensates?
Well, but again, I'm looking over the literature again, and I don't see that there has been ever a confirmed detection of a monopole.
Okay.
I'm looking around. I'm not seeing anything. I was just checking to be sure. Now there are quote monopoles in condensed matter systems, but that's a different thing. That's not talking about a fundamental particle.
Okay, that could be what I'm referring to. All right, next.
There are certainly people that talk about macroscopic black holes are potential magnetic monopoles, but that's a Einstein-Rosen bridge stuff. So
okay, so the monopole problem continued. The pre-inflation monopoles, they would not be stable if they existed, right? So they would have decayed. We wouldn't detect them if they don't exist. They became separated from each other very early on because of inflation, and then have a very, very low density, which I would imply there's not very many of them. And then that it's more likely that they're not stable because we've been looking for them and we haven't found any, according to what Landon's saying. Is that correct?
Yes. So think about it this way: that HRA should have suggest that we should have created monopoles, but if one of the things you get with inflation is between the Big Bang and the start of inflation, you would have either had monopole decay, or if monopoles weren't stable, but if the ones that survived would be at a very low density today, that they were created pre-inflation and inflation separated them out. So now they're so sparse that we're having difficulty finding them.
Yeah.
Gotcha. All right, next slide. The flatness problem. Small deviations in density of matter and energy, omega naught, would create extreme effects in the universe we know today. Why does the universe appear to have a flatness of 1 within 1 part of 10 to the 62? Now, the way I remember this, the local geometry we've discovered is flat. It's up to like 6 sigma or something. You say it's higher. But why does the Big Bang, or why does the inflation theory in Big Bang kind of resolve this flatness problem? Landon?
I mean, one of the things that happened is with the according to the model is that the universe was able to during this inflation period was able to start off with a very okay. Actually, let's back up. What do we mean by flat? That's at first, I guess, one of the first things you have to define. Let's first of all define our terms. When we say the universe is flat, what I guess a layperson's way of saying is that right angles are at 90 degrees, parallel lines don't meet. That for example, a non-flat universe would be where the universe curves in on itself, right? That it looks more like a surface of a 4-dimensional sphere as opposed to being flat everywhere. So when you put a large triangle into the universe, do all the 3 points do the angles of the 3 points sum up to 180 degrees? And you might say, well, of course, because that's what triangles are. Well, if space is curving, then you could have your vertices of the triangles come out much narrower and splay out. So you could have, for example, if you take a surface of a ball and put 3 points on that ball and draw the line, draw the great circles between those 3 points and measure the angles, you won't see a 180-degree triangle.
Now space is not
because
Euclidean, though. I mean, it is curved, though, right?
Yes, but the question is how curved is the overall cosmos? Is the grid of space relatively uniform? I'm not talking about local distortions in it. I'm talking about the overall big geometry of the universe. Is it flat?
Yeah, well, growing up, like when I were to be like Paul Davies, it was said that if you took a telescope and had an infinite amount of power, you could see the back of your head. Does that no longer apply?
I would say.
Go ahead.
I would say no because the observe. Well, so we have our own. Essentially, like any whenever you look off in any direction, like we're at the center of our own observable bubble of the universe. So like. You wouldn't just require infinite power, you would require infinite time and a bunch of other crazy stuff for light to be able to curve not just around the space part, but also the time part. And so I never heard that before. It's an interesting thing to ponder, though.
Yeah, if you were to look through a telescope, I'm trying to just imagine it, you would have to outpace the rate of expansion of the universe in order to try and not even just go faster than the rate that we're expanding, but to be able to then see yourself again. That would
this makes certain
that really is interesting
it
to think
obviously
about.
doesn't take into account acceleration, cosmic expansion. I mean, this is a very simple thing that they used to say, giving just based upon power, not taking into account the time element. But that's only trying to relate the curvature factor, right? So we know now.
Steve, you're correct.
The universe is pretty well.
It's the accelerating universe that says no, you're not going to see the back of your head, even if the geometry would otherwise allow it. I mean, think about when we talk about an object being 5 billion light years away. What do we mean? What we mean is that at the time when light left that object, that we seeing an object 5 billion light years, the universe was of a size such that it took light 5 billion years to reach us. Our now includes their then back 5 billion years ago. But if you want to send a signal back to that same object that was where we saw light traveling to us for 5 billion years, it's not going to take 5 billion years to reflect that light back. It's going to take more than 5 billion years because the universe is expanding. Now, that's not inflation. Inflation's a different thing, but that's expansion of a universe.
Due to dark energy, they hypothesize.
Yeah. Okay. There is this thing. There's this thing we have to talk about in terms of density of matter and energy in the universe, where if again it's that omega naught value. If it's 1, then the universe will be essentially flat. Or, for example, if you had a curvature that was greater than 1, then the surface of space would be would wrap around on itself. Would be enclosed. You might think of it like a sphere. What do you mean with sphere? Well, if you take the dimensions, our 3 dimensions, and map them onto a 4-dimensional sphere, does it reach around and as you say, meet itself? Ignoring the fact that you couldn't see the back of your head, would the geometry cause the lines to wrap around the universe and come back to you? Like going around on the surface of a sphere gives you a 2-dimensional analog of this wrapping around. There is omega less than 0.
Now because of the expansion, right? Because we didn't know the universe was accelerating when I was a kid, by the way. That's actually, I think, 90s or something. So that's relatively new.
Yeah, 98.
Yeah. Okay. So I mean, I wasn't a kid in '98 any longer, unfortunately. But yeah, back in when I was, in high school, that's the way they kind of related it. But anyways, next slide. This is I'm going to turn this one completely over to you guys because I know nothing about topology. So